the recording is started now. We'll see whether it is recorded or not. Anyway, so what is your answer now? Answer regarding the whether the zero, the trivial set is a subfield of, let's say, any finite field in this case, or let's say of a field. Why it is not?
No
It does
multiplicative
not
inverse.
have unity element.
So but
Multiplicative identity नहीं है ना इसके पास.
Yeah, but
Multiplicative
it doesn't need to have. It doesn't need to have a multiplicative identity because f minus 0 does not contain any element.
I think you have a problem here because look at the definition of this field, of the subfield.
Yes, sir. It says that for every x belonging to f minus 0, there exists an x inverse.
But
But
every
f 0 is an empty set. F
so
minus 0 is an empty set. So
it's not a like a, because it doesn't have this unit element. It is not a subfield because it has to be a field first. And in the field, in just a minute, huh? In a field, if you are saying that it is a subfield, then it has to be a field under the same operations, right?
yes,
Now,
sir.
so now can you what is that definition of like multiplicative unit or whatever you are saying, this identity?
for every x belonging to f minus 0, x inverse must exist.
Huh? No,
So, sir,
unit element. When you multiply,
okay. Uh, yes, sir.
Multiply by any element gives same element.
so it doesn't have the multiplicative unit or whatever you say, this unit element. And
Sir, can't 0 act as unit element?
but then you are saying that this is unit element and as well as a. But if it is a unit element, then it should have a. It is a non-zero number, right? You are saying it
Yes,
something
sir.
like that. Then it has to be. It should have a inverse there, but it's not,
Yes.
right?
Why non-zero?
Then you will say that it's a inverse of itself. So see, what I'm saying is that if you want to make it a field, you just check the properties, okay? And you like you see sometime we say that okay, empty set is a, let's say, in just, although we have not introduced this notation, just for just to make an argument here, we say that okay, we have a vector space, then we know that okay, zero is a like a is a basis of or zero is a if you take the span of an empty set, then it is a zero set, something like that. Although if there is no element in that set, but still we say that this is span is zero. Now span of a empty set, how can it be zero? It's not there. There is no element in that. But then we say that this is for the sake of completeness or for the sake of convention. We for the sake of completeness, we make this convention. So here you try to answer yourself whether zero can be a field or not. Okay. So for a subfield, it should have the same zero element as well as the unit element of a field. Now you are saying that zero is a subfield of, let's say, set of real numbers, let's say, because zero is there. Now if you are considering this as a subfield under the same operation, then it should have the same zero and the unit element. If you want to define arbitrary, like you don't consider this as a subfield of something, but you want to define this zero set, a set containing only the zero element, and if you want to say that this is a field, then you just define two operations on that and then you talk about that. Then you can make it a field because just one object, and if you can define two operations on this, then and does these if these operations satisfy these 11 properties, then you say that it is a field. So anyway, you think about it. you are making yourself confused here. Let's move to the this system of linear equation. Okay. So so far I think you have learned a system of linear equation, uh, system of real linear equations. That means the underlying field is the field of real numbers. But here we are not assuming that this linear equation or the coefficient of these linear equations belong to a to the field of real numbers or to the field of complex number. We are just saying that they should belong to a field. This field can be anything. It could be a finite field, infinite field, rational numbers, real numbers, complex number, or any other field. Okay. So suppose that we have a field F. Okay. And then consider consider the problem of n scalars, of finding n scalars x1 to xn that satisfy these m equations. Okay, so you are given these m equations, and you need to find these x1, x2, and so on up to xn, such that these equations are satisfied altogether. Okay, so I'm calling these equations as equation star, where these coefficients, these aij's and bi, for each I and j, they belong to the field F. Okay, so this kind of problem we call as a system of the problem of solving system of linear equations, and these equations star here, these m equations, are called system of linear equations. System of m equations in n unknowns. X1 to xi, x1 to xn, they are called unknowns in this system. Okay, the same system. Let me just go through this terminology. We write the same. We can write the same system using matrices. So this is let's say if I collect all the coefficients in this matrix A, and if I call this let's say A, and then the unknown vector, the vector of unknown, I call this X, and then this vector of these BI's, call this as B. Then the same system you can write as this in this matrix representation, matrix vector multiplication representation. It is called AX equal to, it is AX equal to B, and it is actually the same system. Okay. If I write this matrix here, A bar B, so here this is just a notation here. This is a matrix where the first m times n columns are representing the matrix A here, and the last column is the vector B. And this bar here, I have used this bar just for the notational purpose, just to separate the coefficient matrix A and the vector B here. Okay, this this matrix is called the augmented matrix of the system. This just represent that the first n columns are corresponding to the coefficients, and the last one is corresponding to the vector bi's. Okay, so this is just to separate these A and B. This bar is used just to separate this A and B. Okay, you can look at here. So the vertical bar is used in the augmented matrix only to distinguish the column vector B from the coefficient matrix A. So this A is called the coefficient matrix. If all the elements in the vector B, if all the elements of the vector B are 0, then this system, which is now looks like AX equal to 0, this is called a homogeneous system of linear equations. When B is non-zero, that means if any of these BI is non-zero, then it is called non-homogeneous system of linear equation, right? And any vector y that satisfy this system of equation is called a solution of system of linear equation. Okay, so clearly a homogeneous system always has a solution, which is the trivial solution, the zero solution. It is called zero solution is called the trivial solution because every homogeneous system has this solution. Otherwise it is called a non-trivial solution. Okay, So let us take an example for just for motivation purpose. You have already learned these things. Okay, I just want to go through these things so that we cover this topic. The first thing. The second thing is that you can also recall these things, and we might use some of these things in our following lectures. So as an example, let us consider this system of equation. Three equations in three unknown, and we want to solve this system. Now, how to solve this system? We can try to solve this system by eliminating the variables. So how to do that? So let us do it in these steps. So in the step one, I write this. So in the left hand side, you can see that I have written this system. And in the right hand side, I have written the augmented matrix of this system. Then what I would do here, I'll subtract, I'll try to eliminate some of the unknowns so that I can solve these I can solve these equations. So I will subtract 3 times the first equation from the second. So this is the first equation. I'll subtract it from the second one. This is the first one. I'll subtract it from the second one, 3 times the first equation from the second. And if I do that, then I'll get this one, or you can equivalently write it in this way, in matrix form this way. Then I will further subtract 2 times the first row from third. Then I'll get this modified system, which you can again write in as a matrix form here. And now if I interchange the second and third row, then I'll get this system here, which can again be written as this matrix here. Now clearly from here, from the last system, from step 4, you can easily solve this system. At least you can provide one solution for this system of equation, which is z equal to 2 from the last equation. Then you substitute this z in the second one, you will get y, which is equal to -1. And then when you substitute y and z into first equation, then you will get the value of x. So basically you get a solution, x equal to 3, y equal to -1, and z equal to 2. This is a solution of the system. So what we have done here, we started with a system of equation, then we try to eliminate some of the unknowns so that we get a simpler, we tried to eliminate unknowns from some of the equations. For example, in the third equation, I have eliminated variables x and y, unknowns x and y, and in the second equation I have eliminated somehow the variable x. So this way, so we have tried to eliminate some of the variables in some of the equations, and then when we have some simplified system, then we use some back substitution to find the solution of this system. Okay, so what we can observe here, we can observe the following things here. So the first thing what we did is I have written these two observations. I have written these so that I can provide you these notes, and if you are missing anything, you can just read these notes and you can follow the lecture. Okay, so we found the solution of this system by eliminating unknowns. This is what we did, and by writing as a linear combination. So how did we eliminate this? We write some of the equation as a linear combination of other equations. For example, here, what I did here, I multiplied 3 times the first equation, and then I subtracted this equation from the second one. So what I did is that I wrote the second equation as a combination of first and second. So this we can call at this point as a linear combination, although we have not defined it properly, but let's call this as a linear combination, where you write some of the equations with a combination of other equations. Okay, so here, so what do I mean by linear combination? Multiplying equations by scalars and then adding. So you multiply equations by some scalars and then add them. So this is the linear combination. The second observation you can make is the following, that if I take any solution,
Sir?
so here, yes,
So here the scalar should not be 0.
yeah, it should
Or
not be. If you multiply with 0, you won't get anything.
yes,
So,
sir.
so what is our purpose? So if the scalar should be, so in general linear combination, I said that you multiply with scalars and then add with some equations. But in order to solve this system, you should always multiply with a non-zero. Otherwise, you won't get anything.
Yes, sir.
So yes. So any other thing?
No, sir. Clear.
Okay. So now you can see here from step 1 to step 2, what we did, we subtracted 3 times the first equation from the second one. But then you can observe that if I do it in this way, then whatever solution I have for this system here in step 1, the same would also be a solution of the second one. That means that you can observe here, it's very easy here. You can also observe it in this way, that I have written it in this way. So if suppose, so what I'm saying is that any solution of star is our system, is also a solution of the equation obtained by a linear combination of the equations in star. So if suppose x1 to xn is a solution of star, let's say this is a solution of star. Star means your main system of equation. Then this is also a solution of this equation. What is this equation? This is just a linear combination. This is just a linear combination of these m equations, right? So how would you get this? So you multiply the first one. So I get it in this way. So this is our system of equation star. I will multiply. Uh, I'll multiply the first one with, let's say, coefficient C1. Then the second equation is C2, and so on up to Cm. And if when I do this, so this, what I did, what is linear combination is that you multiply this equation by some scalars. So I'm multiplying, let's say C1, C2, Cm. They can be 0 also here at this point. So if I multiply with these scalars, and then when I add these equations, I'll get a new equation, right? Then when I write this new equation would be of this form. You see here in the new equation, the coefficient of x1 would be c1 a11 plus c2 a21 plus cm am1 up to am1. These are the coefficient of x1. Similarly for x2 and so on. Right? Now you can see that any solution, any set of unknowns like x1 to xn that satisfy this star, this would also satisfy this new equation because it's just a combination, right?
Yes, sir.
So it's very straightforward. So if this is a if x1 to xn is a solution of a star, then it is also a solution of this equation. This is because all these things you can write as a combination of the given equation. So they should also satisfy. This is simple verification. You can do it here. Okay. So these two observations are very important. The first one is that in order to solve the system, we just eliminated some of the unknowns from some of the equations. This is what we tried to do. And the second thing is that in order to do that, we have multiplied some of the equation and then uh, added with some other equations. That means we wrote some of the equation as a linear combination of other equations. And if we do so, then we don't change the solution. The solution set remains same. That's what we have observed. Okay. So let me write this equivalent system. What is an equivalent system? Two system of equations, so two system of linear equations are equivalent if each equation in each system is a linear combination of the equations in the other system. So that means if I have, let's say two systems, ax equal to b and let's say cx equal to d, then I say that these two systems are equivalent if and only if every equations, that means here, as can be written as a linear combination of this one, and every equation here in the second system should be able to written as a linear combination of equations here. So if you can write every equation as a linear combination of equation from the other set, then we can say that it is these systems are equivalent. Okay, both ways. So every equation here should be a linear combination of the other one. Every equation in the other system should be able to return as a linear combination of the first one. Okay, and then from the second equation, you can easily say that this as a result that equivalent systems have the same solutions. Do you agree with that?
Yes, sir.
Yes, sir.
Yes, sir.
It's
Yes,
because
sir.
of the second observation. It's very straightforward. So, anyway, so now with this observation, our aim is to solve the system of equation. So for that, I define three types of elementary row operations. So these are the row operations, and then I'll talk about three particular kind of row operations. So first, let me define what is a row operation, and then I'll say what are the operations we are interested in. Okay. So elementary row operation, what we are doing? Elementary row operation, you can see them as a function from m cross n matrices to m cross n matrices. So you already know some elementary row operation, right? So tell me what is an elementary row operation? What you have learned? So let me write it here. Yeah.
One is interchanging the
Interchanging
rows.
the rows.
Yes, please. Can you please repeat?
Yeah, interchanging the row first, and second one is scalar multiplication of any row, and third one is scalar multiplication and adding or subtracting any other equation.
Okay. So you are saying that these are the three operations you have. Can we talk about like more row operations? So these you have talked about three operations, three kind of operations you said, and you said that these are row operations.
So
But
we
if
can
I
multiply and divide. So we can multiply and divide with the constant other than 0.
other than so it's just like the same thing as a
Scalar
multiplication,
multiplication.
Yes,
Yes, sir.
the scalar multiplication.
scalar multiplication.
Yeah. So it falls in that. But what I'm saying is that can you define these operations? So how to define these three operations? You are saying that just multiply interchange the two rows, then this is an operation, then you just
So
Sir,
if
like Ri goes to
if we,
C times Ri.
so what I want to say is that you are defining some operations, right? These operations are defined on a matrix.
Sir,
So
we
can you
can
define?
define that from linear combination of this one.
So what I'm saying is
sir,
that
if we
can you?
define some operation, it does not lose its originality, then this operation can be say elementary row operation.
So what do you mean by originality? So how do you define this originality?
Sir, the solution set
So the
remains same.
solution of the matrix will not change after the applying the operations.
This because you have learned these things, right? You are recalling some of the results which you have
Yes,
learned.
yes.
सर जो
What I'm
ऑपरेशन हम
saying,
डिफाइन करना चाहते हैं उससे अगर आइडेंटिटी एलिमेंट पे परफॉर्म करके उसे प्री मल्टीप्लाई करते हैं उस मैट्रिक्स तो वो परफॉर्म हो जाएगा ना.
no. So what I want to say is that
Sir, your sound is not loud.
what I'm saying is that how to define. So when you are saying that these are operations defined on a matrix, right?
सर इसे लीनियर कॉम्बिनेशन में डिफाइन करेंगे.
नहीं linear combination से define कर देंगे, but can you say that these are functions from the set of matrices to set of matrices? So these are functions only, right? So you are saying that when you interchange two rows, so you are given a matrix. This is a matrix. Now when you apply something on this matrix, that means you are doing something, and then you will get something as an output. So you can define this as a function, right? So you are given a matrix that should be your input. Then you do something, that means you perform some operation. This could be whatever you are saying, interchange two rows. When you interchange two rows, you will get a new matrix, right? So it's like you are given x as the first matrix. When you perform the operation, that means the function you are applying on this, then you get fx. So fx is the matrix which is obtained by performing the sum operations. So you can write a elementary operation as a function from the set of matrices to another set of matrices that satisfies certain things. For example, you just interchanged any two rows and then you will get another one. So that is a function. So the first function is actually interchanging any two rows of a given matrix. You will get another matrix. So it's a function, it's a well-defined function from set of matrices to another set of matrices. The second one is a scalar multiplication. You can multiply any row of this of the given matrix, and then you will get in another matrix which is obtained by multiplying some of the row with a particular constant. So it's a scalar multiplication. And similarly you get the third one also, which is like adding two rows. So a row operation is actually a function from the set of matrices to another set of matrices. And in particular, we are interested in three type of these elementary operations, and we define these three type of elementary operation as interchanging two rows. That I can write it as let's say if Ri and Rj means ith row as Ri, and if I denote jth row as Rj, then interchanging Ri and Rj is the first operation. I can call this as elementary operation. I can also write it in this way. So this is just because we can sometimes use this notation. So let's say E1, if I multiply E1 when I apply on A, so it's like A goes to E1A. So E1 is the first type of elementary operation. So you can see that I can write it as a so let me just use different color here. So I can write it as, let's say, some rows goes to another row, but I know that it is obtained by the first type of elementary operation. So it's just like as a function, you were given a matrix A, and then you have applied the first type of operation, and you get another matrix. I call this E1A. E1 is the first operation I define. And similarly, you can talk about this. This is just for the understanding purpose that we can consider them as a function. Okay. Anyway, so then we have the second operation, which is multiply a row Ri by a non-zero constant. So I can write it as this one. So ith row is multiplied by a constant. So you can see that when I write this, you can see that this is sort of a function. So ith row is now replaced by CRI, and this is a new, here we have a new matrix. Similarly, add a multiple of a row Rj to another row Ri, so that you can write it in this way. So Ri has now replaced as Ri plus Crj. So in the new matrix, the ith row is actually Ri plus Crj. Okay, so these are the three operations. We call them as a elementary operations, and for these we have a result like for each elementary operation E. So this E can be anything, any of these three. So for each elementary operation, so with this abbreviation I mean elementary operation. So for each elementary operation E, this E can be any of these three type of operations. There exists an elementary operation, let's call E1. This is just a notation, E1 of the same type as E, such that when I apply this E1 on E of A means this is A, the given matrix. E of A is the matrix which is obtained after applying this operation E on A, and then E1 of E of A is actually applying E1 on E of A. So this is then we get the same matrix A, or if you apply in the other order, then also you get the same matrix A. If this is the case, then we say that E1 is the inverse of ER, elementary operation E. So what this result says? This result says that if we have an elementary operation E, then for that elementary operation, we can always find an elementary operation that does undo the work of the previous operation. So, do you agree with this this result?
Yes,
Yes.
sir.
Now, can you tell me how to prove this? This is the result. Now, can you prove this? Yeah, can you prove this? Your voice is not clear. There is some disturbance.
Sir, can scalar be 0?
No, scalar cannot be 0. No? Here it can be 0. I mean, just for the sake of definition. But since we want to solve this, in the definition of linear combination, the scalar can be 0. Here we have written that it's a non-zero. So you can see here in the definition itself,
Yes.
it's written non-zero.
Sir, then the first property has an inverse by just interchanging R1 goes to R2 or R2 goes to R1.
So that means, so let me do it in this way. So you are saying that the first one, so let me write this. Okay, so the first one, you are saying the first one is Ri interchange with Rj.
Then the
So
inverse
this is our E. So what would be E1 now? You tell me for the first one.
Rj goes to Ri.
So the same thing actually. Again, you interchange Rj and Rj.
Yes.
So it is the same thing, right? So I agree. So this is fine. So this is the first one. When it is second one, then the second elementary operation.
Find the inverse of the scalar, that is 1 upon C.
So when E is Ri goes to CRi, then the inverse E. So if this is E, then the E1 would be Ri goes to 1 upon CRi.
Yes.
Yes, sir.
What about the last one?
So for the last one,
so the E is Ri goes to Ri plus CRj. This is your E. So what would be E1?
1 upon
Ri minus CRj.
Yeah, tell me, what would be E1? Ri goes to where?
Ri minus CRj.
Ri minus
CRj.
Ri minus
CRj.
CRj? Are you sure?
CRj. Yes, sir.
CRj or 1 by
1
CRj?
by CRj.
By CRj.
1 by
1 by
CR.
CRj.
1 by C.
Right. So this way you can say that every operation has a inverse operation. Every elementary operation has an inverse. Now this, if you look at the elementary operation as a function, then you can easily say that there is also inverse function that undo the job of E, the original operation. So now I think we have time, so we will stop here and then we'll continue on system of linear equation in the next lecture. So I'm sorry that we lost about 10 to 15 minutes in between. So we'll try to cover this whatever time we lost today. We'll try to do it some other time. Okay. So we can stop here now. If you have any doubt, you can ask. Otherwise, we'll stop.
Sir, in third operation, it should be Ri minus CRj.
Yes, sir.
Ri minus?
CRj.
So C times Rj. Right. It's a CRj, not 1 by C. Would be
Yes, sir.
CRj, right? You are right. It would be CRj. You just verify that's all. Because we are adding CRj, so we have to subtract CRj.
Yes. Thank you, sir.
Thank
So
you, sir.
any other thing?
Thank you, sir.
Okay.
So we
fine.
have another class today.
Yes, yes. Please go. Please proceed.
So we get the notes on MS Team.
You will get the notes. I'll upload it on Moodle, and I'll send
Okay, sir.
an email regarding that.
Okay, sir.
Okay, sir.
Okay,
Okay,
then see you next Tuesday.
Okay, sir.
Okay,
Yes,
sir.
sir.
Bye bye.
Thank you, sir.
Thank you, sir.
Okay, sir. Thank
Have
you,
a good
sir.
day.
Thank you, sir.
Thank you, sir.
सर
Yes.
सर आपने जो क्वेश्चन दिया था कि एवरी सब फील्ड हैज अ सब मतलब मस्ट कंटेन एवरी रैशनल नंबर।
Right.
तो सर उसमें हम ऐसे भी कर सकते हैं कि हम एज्यूम कर लेते हैं कोई ऐसी एक सब फील्ड है जो सभी रैशनल नंबर को कंटेन नहीं कर रही है।
हाँ.
तो उसमें मान लेते हैं कि एक रैशनल नंबर पी अपॉन क्यू जो सब फील्ड में नहीं है। तो प्रॉपर्टीज ऑफ रैशनल नंबर वहां पे लगा के कि पी एक इंटीजर है और क्यू एक नेचुरल नंबर है। If p by q does not belongs to subfield, so this implies either p does not belongs to subfield or 1 by q does not belongs to subfield.
Right.
Okay, sir. If p is any integer which does not belongs to subfield, then it contradict about the closure property of 1 element 1.
You can say that not element 1, but you can say that it violates the closure property of that subfield itself.
Okay, sir.
Because that 1 is actually in the field now, so it is a closure property of that.
Similarly for sir 1 upon q also.
Right. It's the same thing. You are arguing in a different way, but it is actually the same thing.
Okay. Thank you.
It's actually the
Sir.
same thing, but it is correct. Yes.
Sir,
Yes. Yes. I can hear you.
आपने ZP के अलावा कोई सब